Okay, what you can see on your notes is we're going to study the effects that temperature has on reaction rates. This is actually a point that they've changed on the AP test. No longer do you have to do calculations with this. It's just going to be about understanding what is occurring. The first part of this is just really about understanding why the reaction will even take place in the first place, regardless of changes in temperature, just at whatever temperature. The first thing we have to understand is something called collision theory. Now, as you see on your paper, collision theory simply states that the reaction rate will be equal to the frequency of effective collisions between reactants. That word effective is extremely important. If you've ever seen like a car accident where just a little fender bender, people just kind of bump into each other, there's no real damage done, that would be like an ineffective collision. A big car accident where you see all the mangled mess of cars, that would be an effective collision by our terminology. So if you take a look at your what's necessary, I guess is what I should say, for an effective collision, there's really two things. First of all, they have to hit hard enough. Okay, that's number one. The molecules must hit with sufficient energy. That energy is called activation energy, and it's symbolized by that right there, the big E standing for energy, and then the little A standing for activation. You can see the definition there on your paper. I don't have it on the board, but it's there on your paper. You might underline it. It's the end of that little paragraph. So they have to have enough energy. So if the necessary activation energy is, 200 kilojoules per mole, and the particles only have 100 kilojoules per mole, they're not going to have as many sufficient collisions. Those collisions aren't going to be effective. The second thing is they have to hit each other correctly. They have to hit the right parts of the molecules, have to actually collide. So if you take a look at the example in that little box you have there, the first picture is showing you that the A2 and B2 molecules are lined up correctly to be able to bump into each other to react. Now, you don't have to know what the correct orientation is. You might look at the two examples, the correct and incorrect orientations there on your paper, and think, well, how was I supposed to know they were supposed to collide like that instead of like that? Well, don't really worry about it. You're not going to be given pictures and say which one is correct, okay? You just need to know that they have to hit each other the way that they're supposed to. So they have to hit hard enough, and they have to hit each other in the correct orientation. That's what makes an effective collision. Now, we also have these things called reaction profiles, which you can see on your paper. We have two different ones shown on there. Let's look first at let's start with what it's graphing. It's graphing the potential energy. You can see these graphs in my paper just say energy. Really, it's potential energy. You might mark that on your paper as well. So it's an indication of the potential energy that your reactants and products have during the very beginning, before they've reacted, what's happening during, and then what ends up happening in the end. So it gives us a good visual picture of what's occurring with the potential energy of the particles. The other coordinate, the x-axis, is called the reaction coordinate. Some people refer to this coordinate as, they call it the extent of the reaction. So really, it's kind of like time. We don't measure it in time. We measure it as to be what part of the reaction we're at, but it's really telling you what part of the reaction. So when you're closer over here, this is going to be at the beginning of the reaction, and this is at the end of the reaction. That really is what it is telling you. So if you take a look, let's start with the one on the left side. You see here you've got a flat line representing the potential energy of the reactant. So this is where they're just reactants. They haven't seen each other yet. There's two different, I'll bubble this one in, say these two things are sort of looking at each other, the potential to react. And they might be starting to travel towards each other. And once they start to travel towards each other, their potential energy starts to increase. So during this whole segment of the graph right there, we're talking about the time when these two are traveling towards each other. Okay, so the potential for a collision is increasing, and that's why their potential energy is increasing. Now, when we get to the top, that's where they actually end up colliding. Okay, this is the collision And as long as they had enough energy to get to the top and they hit each other right, then that's going to be an effective collision. You'll see on your paper that that is called the activated complex up here at the top. Again, right here, this is called the activated complex or the transition state. I have both of those terms there on your paper for you in that little paragraph above. So that transition state or activated complex represents the maximum potential energy that we have. When they collide, they're at their highest potential energies. Then once they collide and the collision was effective, those particles, the new particles, whatever the product is, let's say the product is now, do it this way, oops, whatever the products are, so some new substances have formed, and they're going to be moving away from each other. So you see the potential energy is going to be going down until you get to this line, and then that's where they're completely far away from each other and they're not existing and talking to each other at all. So again, it's just representing the different stages of the reaction. At the beginning here, it's all reactants. At the end here, it's all products. And this is the points where they're coming towards each other, reacting, and moving away from each other. And all reaction profiles have that basic setup. Okay, you'll have your beginning energy, your ending energy, and then it'll graph for you what it looks like in between. Now, there's two different profiles on your paper here. The one on the left side you can see is labeled as endothermic, and the one on the right side is labeled exothermic. The reason for that has to do with where those potential energy lines are. Take a look back at the one we've been working with. You see how low the energy is for the reactants, and the final products ended up with more energy. Okay, so because the reactants had less energy than the products ended up with more energy. It had to have absorbed energy. Must have absorbed energy in order for the products to end up with more energy. But look at this one. This one started, the reactant energy was really high. They move towards each other, they collide, right? That's the activated complex or the transition state. And then when they're all said and done, the products are way down here. So you end up with way less energy for the products. So they must have released energy to be able to have less energy in the end, over there on the far right. There's also some other things we can measure on these reaction profiles. Let me erase a little bit here. So if you're looking at a reaction profile, you can actually make some measurements if you were given the numbers along the axes. That activation energy that we discussed, the minimum amount of energy necessary for a reaction to take place, that's measured from this line where the reactant energy, potential energy starts, up to the very tippy top of the graph. That is the activation energy. That's the minimum energy needed to get over there. You can think of it like riding a bike. There's a minimum amount of energy needed to ride up over a big, huge hill. If you don't have that much energy, maybe you only have enough energy to get to here, the reaction's not going to happen. It's going to go back down and stay as reactants. But if you have enough energy, it'll get up over the hill, the reaction will occur. So that's the activation energy. So for this one, it's from here up to the tippy top. Okay, so that's the activation energy. We can also measure delta H. Delta H. Remember, delta H is the change in heat. The change in heat is simply going to be from the reactants line to the products line. So from here to here is your delta H. On this one, it's from here to here is your delta H. And again, when you do products, we do products minus reactants, we end up with a negative delta H here, which makes sense because we said that was exothermic. If we do products minus reactants, we would end up with a positive delta H, which again makes sense based on what we've seen. Also, the height of the hill, okay, the height of that graph, the activation energy, can actually tell you some things about the rate as well. This one here has a much larger hill than this one. Okay, this one here, the activation energy, the one on the left side, the activation energy will be much higher. The higher the activation energy, the slower that reaction is going to be and the lower its K value is going to be. That's on the second bullet down below. And if you think about it, it makes sense. If it requires more energy to occur, then not as many collisions will be effective. Okay, so the one on the right side, this one here, less energy means more effective collisions. That's going to be a faster reaction. So you can actually look at reaction profiles and tell how fast a reaction is going to occur as well. Okay, so let's take a look. I've written sufficiently all over these ones. Let's take a look at one that shows actual molecules instead of my silly drawings. So you see in this one here, you have N2, I'm sorry, NO2 and CO, okay? Initially, this line right here is representing their potential energies when they don't really know the other one exists. That's why it's constant. As soon as they start to move towards each other, that's when we're going to get this segment of the graph right here, okay, moving towards each other. This is the collision. So as long as they had enough energy to actually get up there, then they'll form the activated complex. And then this is them moving away from each other, the new products, okay? And then here are the products not interacting with each other at all, and that's why this line is constant. Again, looking at this graph, you can see that we have products with a lower energy than our reactants. By the way, there was issues here. I'd fixed this on yours. So this should just say delta H, and this should just say EA. Sorry, I fixed it on yours and didn't fix it on mine. So we can measure the delta H difference here. Actually, this one has numbers over on the side, so we could actually measure it. The activation energy here looks like it's about, I don't know, 120 maybe. And then kilojoules per mole, and then the delta H would be the difference between here and here. So you would do negative 210 minus 100, so we'd get negative 210 or so, 220 maybe. Again, not a great graph. Usually they don't have us actually measure the numbers. They'll ask you more generic questions, like looking at this graph, is this reaction endothermic or exothermic? And you can see that the products have less energy than the reactants. So it had to have released energy for that to have happened. And if it released energy, then that means it's exothermic, okay? Or they might ask you to graph the activation energy, compare the activation energy of two different things, that type, okay? So that's what it looks like. You should be able to look at one and kind of make all those interpretations that are listed on the front of your notes down at the bottom. Then the last part, and again, this is new. Usually I have to teach about actual temperature conversions calculations. We have a big, huge equation called the Arrhenius equation that does that for us, but they're saying no more. They're saying they just want you to understand the relationship between temperature and reaction rate, and K. So here's the basics. As temperature increases, the rate of the reaction will increase, and so will K. K and rate always are intertwined with each other. If K is going up, the rate's going up. And temperature causes reaction rate and K to increase because the higher the temperature, the more effective collisions you're going to have. You're going to have more collisions with that activation energy. You're going to have more collisions, so therefore increasing the chance that they're going to collide in the correct orientation. So higher temperature means faster reaction rate and a higher K. And then, of course, the opposite's true. If you decrease the temperature, you're lowering the reaction rate and decreasing the value on K. And they want you to understand that on a conceptual level. So a question literally will say something to the effect of, if you increase temperature, what happens to the rate of the reaction and what happens to the value of K? You know, something to that effect. All right, so you have some homework problems to do with these. There's some review on there as well. And make sure you do your Socrative as well and send in those questions, and we will discuss anything that we need to. Thanks.